Welcome to the Deep Dive. Today, we're diving into some fascinating statistical concepts based on the notes and excerpts you've sent us. Looks like you're gearing up for some pretty serious data analysis. We're here to help you break it all down. We'll be covering a whole range of topics: standard error, hypothesis testing, even overfitting and linear regression. Ready to jump in?
It's great to be here. Yeah, these are some really fundamental statistical ideas. Getting a good grasp of them can really take your data and analysis to the next level.
Okay, let's start unpacking all of this, starting with standard error. You highlighted two ways to calculate the standard error of the median: bootstrapping and the formula for normally distributed data. So what's the big difference between these two?
You're right, both methods give you a way to measure the variability of the median, but they go about it differently. Bootstrapping, well, it's a resampling method that's really handy when you don't want to or you can't make assumptions about the underlying distribution of your data. Imagine you're creating like a bunch of mini data sets from your original data, and then you calculate the median for each of them. Bootstrapping is essentially looking at how much those medians jump around. That gives you a robust estimate of the standard error.
So it's like running multiple simulations to see how stable the median is. Makes sense. One thing that really stood out in your notes was this idea that the standard error of the median can sometimes be bigger than the standard error of the mean, even though typically we think of the median as being less sensitive to outliers. That seems kind of counterintuitive, doesn't it?
That's a great point. It shows that even concepts that seem basic in statistics can have some surprising twists. Yeah, the median itself might not be wildly affected by outliers, but think about the bootstrapping process. Some of those mini data sets we create might end up with pretty different medians because of how the outliers are randomly included or excluded. That variation can lead to a bigger standard error for the median.
So it's not just about the measure itself, but also the method we use to calculate its standard error. Important takeaway for anyone working with, real-world data. And speaking of real-world data, you mentioned improving two-factor ANOVA using a randomized block design. Can you explain how this technique helps us get results that are more, meaningful?
Absolutely. Let's say you're studying how two different fertilizers affect plant growth, but you already know that the soil quality in your field is kind of all over the place. If you just randomly assign plants to the fertilizer groups, that variation in the soil, well, it could end up hiding the real effects of the fertilizers.
It's like having some runners starting a race on a paved track and others starting on a rocky trail. It wouldn't be a fair comparison.
Exactly. A randomized block design, it's kind of like grouping the runners based on the type of terrain they're running on and then randomly assigning them starting positions within those groups.
Makes sense, right? So for the plants, we'd first group them based on similar soil quality, and then we randomly assign them to different fertilizer treatments within those soil blocks. Doing that reduces the variability within each treatment group, and that makes the comparison between the fertilizers more accurate. So it's about controlling for, like a known source of variation so we can zero in on the effects we're actually interested in.
That's clever. Now, switching gears a bit, let's talk about a common trap in data analysis: overfitting in linear regression. You specifically mention a scenario with a data set that has 1,000 samples and 900 features. What's the potential issue there? That's a perfect example of what can happen when you have way too many features compared to the number of samples. It's like trying to write a 10-page essay based on a single paragraph. You end up kind of stretching that tiny bit of information way too far and making connections that aren't really there.
So instead of capturing the real signal in the data, the model is picking up on noise. And that could lead to predictions that are just plain wrong when you try to apply the model to new data.
Right. Imagine a student cramming for a test, just memorizing the answers instead of actually understanding anything. They might ace that one test, but their knowledge won't work anywhere else.
Makes sense. So how do we avoid falling into this memorization trap? You highlighted some regularization techniques: Lasso, Ridge, and Elastic Net. Can you break down how they help us avoid overfitting?
These techniques are like adding a penalty to the complexity of the model. Essentially, it discourages the model from getting too excited about every tiny detail in the data. Think of it like adding a little friction to the model fitting process so it doesn't go completely off the rails.
So it's a balancing act, right? We want a model that fits the data well, but it also needs to be simple enough to generalize to new data. Could you give us a bit more detail on how Lasso and Ridge differ in their approaches?
Sure, Lasso, which uses L1 regularization, has this special ability to actually shrink some of the coefficients in the model all the way to zero. What that means is that Lasso can do feature selection.
Hmm.
It identifies the most relevant features and basically throws out the less important ones. It's like a sculptor chiseling away at a big block of marble to reveal the form hidden inside.
So that gives you a simpler model that's easier to interpret. What about ridge regression? What's its style?
Ridge regression uses what we call L2 regularization, and it's a bit gentler. Instead of forcing coefficients to zero, it shrinks them proportionally. So all the features can still contribute, but it prevents any single feature from dominating the model. It's like adjusting the volume knobs on a sound system. You want a balanced and harmonious sound.
Both techniques are aiming for simplicity, but they get there in different ways. Okay, now you also brought up a really interesting question about comparing means. You asked, can we just compare the mean price of shoes from last year to this year to see if prices have changed? Seems simple enough, right? Why might this be problematic?
It's a great question that highlights how important it is to, think about the context of your data. Your notes mention that shoe prices aren't all the same. They vary a lot based on brand, style, gender, even age group.
It's like comparing apples and oranges if the types of fruit in your basket have completely changed between the 2 years.
Exactly. If the mix of shoes being sold is different this year compared to last year, simply comparing the overall means can give you a really misleading picture. Let's say this year there's suddenly a huge demand for like those expensive designer sneakers. The overall average price might jump up even if the prices of other types of shoes haven't changed at all.
Yeah, that makes total sense. So how can we get a more accurate view of price changes when we have all this variation within the data?
That's where t-tests can be super useful. They let you compare the means of subgroups, giving you a more detailed look at what's happening. Instead of comparing the average price of all shoes, you could compare, for example, the average price of men's running shoes this year to the average price of men's running shoes last year. And you can do the same for women's sandals, kids' shoes. You get the idea.
So essentially we're controlling for those confounding variables, the different types of shoes, to get a clearer view of the real price trends within each category. It's a great example of how thinking carefully about the structure of your data can lead to a much more insightful analysis. It's really interesting how those seemingly small variations within a dataset can make a big difference in our analysis. Speaking of subtle differences, you've also included some notes on identifying the distribution of data. What are some ways we can figure out whether our data actually follows a specific distribution?
Oh yeah, there are a bunch of tools we can use for that. We've already touched on probability plots, which give you a nice visual way to see how your data compares to a theoretical distribution. Like
Yeah.
if those points line up on the plot, you have a good indication that your data might be following that distribution. But sometimes you need something, well, a bit more formal, a quantitative way to really test that goodness of fit.
Right, so we're looking for something beyond just eyeballing a plot. What kind of statistical test can we use for this?
A common one is the Anderson-Darling test. It's really good at catching even slight deviations from normality, like it's super sensitive.
And you also mentioned Minitab and ML estimation. Could you tell us a little more about those? How do they relate to identifying the distribution of our data?
Sure, Minitab is a statistical software package. It's got all kinds of tools for data analysis, including those goodness of fit tests. Think of it like a super-powered toolkit for exploring and understanding your data. And ML estimation, short for maximum likelihood estimation, is a method for estimating the parameters of a specific distribution. It basically helps you find the parameters that make the observed data the most likely.
So these tools can help us pinpoint the most likely distribution that our data follows, which is important for, like, choosing the right statistical methods down the line, right?
Exactly. It's all about making sure you're using the right tools for the job.
Now, let's dive into a concept that's super important for designing good research studies and experiments. Power analysis. I know you're all about efficient learning, so how can we break this down quickly but still make it stick?
I like to think of power analysis as plan a fishing trip. You want to make sure your net, that's your sample size, is big enough, and you've got the right bait, your study designed to actually catch the fish, which is the effect you're looking for. It's all about maximizing your chances of finding something statistically significant if it really exists.
It makes sense. So to avoid coming back empty-handed from that fishing expedition, we need to understand type I and type 2 errors.
You got it. I love the analogy you used in your notes. Convicting an innocent person, that's a type I error. Or letting a guilty person go free, a type 2 error. In research, a type I error means you conclude there is an effect when there really isn't. And a type 2 error means you miss a real effect that's actually there.
So power analysis helps us balance those risks,
Right.
basically guiding us on what sample size to use and the overall design of our study. You mentioned the key parameters for power analysis: significance level, effect size, and power itself. Quick recap, what do each of those represent?
Sure thing. Significance level, we usually call it alpha, is like setting the bar for how strong the evidence needs to be to reject the null hypothesis. It's basically the probability of making that type I error.
So it's like setting the standard for how convincing our evidence needs to be before we say, hey, this is real. What about effect size? How does that fit in?
Effect size is all about the magnitude of the effect we're looking for. Think of it this way. The bigger the fish you're trying to catch, the easier it is to spot, right? A larger effect size means you might need a smaller sample size to detect it confidently.
So it's about the strength of the signal we're trying to find in the data. And finally, what about power itself? How does that relate to everything else?
Power is the probability of finding a real effect if there is one. So higher power means you're more likely to catch that fish or to detect that effect.
So power analysis is like a roadmap for setting up your study for success. You figure out the level of power you want, consider the expected effect size, and then you can calculate the sample size you need. It helps avoid wasting time and resources on a study that's underpowered.
Exactly. It's a really valuable tool, especially in research.
Okay, let's try applying all of this to a common scenario: testing whether a coin is fair. You pose this interesting question. You flip a coin 10 times and get 8 heads. Does that mean the coin is definitely unfair?
It might seem that way, but 10 flips, it's a pretty small sample, right? Like in that fishing example, you could get lucky and catch a bunch of fish, even if there aren't that many in the lake.
So, statistically speaking, how do we figure out if the coin is truly rigged or if it's just random chance?
We've got to consider the probability of getting 8 or more heads, even if the coin is perfectly fair. If that probability is pretty high, then we can't rule out chance as the explanation. But if that probability is really low, then yeah, we might start to suspect that the coin's got some tricks up its sleeve. We can actually calculate that probability using the binomial distribution. It tells you the probability of getting a specific number of successes, like heads, in a set number of trials.
So, it's about figuring out how likely it is to see a result this extreme, even if nothing fishy is going on.
Yeah.
And if we want to take it a step further, we can use a t-test, right, to formally test the hypothesis that the coin is fair.
You got it. A t-test works here because we're comparing the proportion of heads we actually got, 8 out of 10, to what we would expect if the coin was fair, which would be half heads, half tails.
Okay, that's a great illustration of how we use hypothesis testing. Now, you've also included some notes on causal inference, which can be a bit tricky. You specifically asked if taking a random sample of 1,000 people in Mountain View and running an ANOVA would be a good way to figure out if going to college actually causes people to earn more money.
That's a really important question because it gets to the heart of how we establish causality, not just correlation. Just because we see a relationship between two things, like going to college and having a higher income, doesn't automatically mean that one thing causes the other. There could be all sorts of other factors involved.
So what's the issue with using that random sample, a Mountain View, and then doing an ANOVA?
Well, first off, the sample itself might not be representative of the population we're interested in. Mountain View is a pretty unique place, lots of tech companies, high salaries. That could definitely skew the income distribution and hide the real relationship between college and income in the bigger picture.
Right, so sampling bias is something we need to be really careful about. Anything else to watch out for?
Absolutely. We've got to be super careful about what we call confounding variables. Those are factors that influence both college attendance and income. They can really muddy the waters and make it tough to separate the effect of college alone. A classic example is family socioeconomic status.
Oh yeah, kids from wealthier families are more likely to go to college, and they probably have access to more resources and opportunities that could lead to higher earnings, even regardless of whether they go to college.
Exactly. So the relationship we see between college and income might be what we call spurious, meaning it's actually driven by those hidden factors. It's not a direct cause and effect link. So how do we tease apart all of those influences and get closer to proving that going to college really does cause higher income?
Yeah, that's a million-dollar question.
Well, one really powerful approach is A/B testing, which is all about randomly assigning people to different groups. In this case, you'd have a group that goes to college and a group that doesn't. Then you compare their outcomes over time. Random assignment is key because it helps make sure the groups are pretty similar, at least on average, when it comes to all those potential confounding variables.
So A/B testing is like a controlled experiment, right? We're basically manipulating the thing we're interested in, going to college, while keeping everything else as constant as possible.
Exactly. It's a gold standard for proving causation, but the catch is you can't always randomly assign people to big life choices like that. It wouldn't really be ethical.
Yeah, I get that. So what are some other strategies for dealing with these challenges, when A/B testing isn't possible?
Well, a lot of times we have to rely on observational studies and different statistical techniques that try to control for those confounding variables as best we can. Regression analysis is a common one. It lets you statistically adjust for the impact of those confounding variables to try to isolate the specific effect of the thing you're interested in.
Now let's shift gears to a different kind of puzzle. Estimating the total number of ad installations when all you have is data on installations for a sample of users. It seems like you're really interested in the idea of using statistical estimation to figure things out about a larger population based on limited information.
Yeah, it's fascinating how much we can learn from a sample even when we don't have the full picture.
You specifically mentioned the difference between sampling with and without replacement. Can you refresh our memory on how those work and why it matters in this scenario?
Sure, imagine you're picking marbles out of a jar. Sampling with replacement means you pick a marble, look at it, and then you put it back in the jar before picking another one. So each time you pick, every marble still has an equal chance of getting chosen. Sampling without replacement means you pick a marble and you don't put it back. So with each pick, the pool of marbles you're choosing from gets smaller.
Ah, so in the ad installation example, sampling with replacement means the same user could get picked multiple times, but sampling without replacement means each user is only counted once.
Exactly. And the way you sample affects how you estimate that total number of installations. If you sample with replacement, you can use the proportion of installations in your sample to estimate the total in the whole population directly. But if you sample without replacement, you need to adjust for the fact that the group of potential users shrinks as you go.
Right. The way we sample has a direct impact on how we extrapolate from the sample to the entire population. Okay, you mentioned confidence intervals earlier. How do those fit into the picture when we're making estimates?
Confidence intervals are super important because they help us quantify the uncertainty that always comes with making estimates. Instead of giving a single number for, say, the total installations, we create a range around that estimate. And we can say something like, we're 95% confident that the true value falls somewhere in this range.
So it's like acknowledging that our estimate isn't perfect. It's more like a plausible range based on the information we have. You also mentioned two ways to calculate these confidence intervals: traditional methods and bootstrapping. Can you remind us of the key differences between those?
Sure. Traditional methods rely on assumptions about the distribution of your data and then use formulas from statistical theory to calculate the confidence interval. It's like following a tried and true recipe. If your ingredients in your oven behave the way they're supposed to, you'll probably end up with a good cake.
It's a great analogy. So what about bootstrapping? How does it differ from that traditional recipe-based approach?
Bootstrapping is more data-driven. Instead of depending on those preset formulas and assumptions, it uses the data itself to generate a whole bunch of estimates. That gives you a more customized and often a more robust way to build confidence intervals. Think of it like experimenting with different cake recipes and adjusting the ingredients based on how each one turns out.
So you're basically letting the data show you how much uncertainty there is, instead of just imposing a theoretical structure on it. And that could be really helpful when you're working with real-world data that might not perfectly fit those theoretical assumptions.
Exactly. Bootstrapping is a really handy tool when you're dealing with those messy real-world data sets.
Okay, so we've talked about estimating those unknown quantities like the total number of ad installations. It makes me wonder, though, is there a way to figure out which estimate is the best, the most likely?
That's where maximum likelihood estimation, or MLE, comes in. It's a really powerful method for finding the values for the parameters in your model that would make the data you actually observe the most likely. It's kind of like solving a puzzle and finding the pieces that fit together in the most seamless way.
So it's about finding the estimate that maximizes the probability of seeing the specific data we have. Makes sense.
Right. And remember, even with MLE, we still need those confidence intervals to express the uncertainty associated with our estimates.
I think there might be a connection between this idea of sampling with and without replacement and the prisoner's dilemma, which we talked about earlier.
Oh, interesting. How do you see those connecting?
Well, in the prisoner's dilemma, whether the prisoners cooperate or betray each other determines the outcome. And similarly, in sampling, whether you replace a sample after each selection changes the probabilities, which then affects the conclusions we draw about the whole population.
I see what you mean. It's like the choice of sampling method, just like the prisoner's choices, has a ripple effect on the final analysis. It's cool how these different concepts can sometimes overlap like that.
It all boils down to making strategic decisions, right?
Sure.
Whether we're talking about hypothetical prisoners or dealing with real data.
Hmm.
And speaking of strategic decisions, let's revisit that scenario of trying to figure out if going to college actually causes people to earn more money.
Right. That's a classic example of trying to disentangle correlation from causation, which can be tricky.
You specifically question the validity of randomly sampling 1,000 people in Mountain View and then doing ANOVA to answer this question. What are the potential pitfalls there?
Well, that example highlights how important it is to think about sampling bias and those pesky confounding variables when we're trying to prove cause and effect. Mountain View, as we talked about, is unique, lots of tech folks, higher incomes. It might not be a good representation of the general population.
So the income distribution in Mountain View could be skewed compared to other places, making it tough to apply the findings more broadly. What about confounding variables? How do those complicate things?
Confounding variables are tricky because they're related to both going to college and earning more money, and they can make it almost impossible to isolate the effect of college alone. We talked about family socioeconomic status earlier. That's a big one.
Right, so it's tough to tell if the link between college and higher income is really because of the education or if it's just reflecting those existing advantages.
Exactly. And to make things even more complicated, there are often multiple confounding variables at play. It's like trying to untangle a giant knot.
So how do we try to control for these confounding variables when A/B testing, which is like the gold standard for proving causation, isn't a possibility?
It's a challenge. We often rely on observational studies and statistical techniques that aim to adjust for those confounding variables as best we can. Regression analysis, which we mentioned earlier, is a powerful tool for that. It allows us to statistically control for the impact of those confounding variables so we can get a clearer picture of the relationship we're really interested in.
Okay, so it's like trying to filter out the noise to get a clearer signal.
Precisely. And it's not always perfect, but these techniques can get us much closer to the truth.
It sounds like causal inference is a bit like detective work. We're trying to piece together all the clues to figure out what's really driving the patterns we see in the data.
That's a great way to put it. It takes careful observation, a deep understanding of the data, and a willingness to consider alternative explanations and potential biases.
Now let's dive back into the world of identifying data distributions. You've shared some different techniques for figuring out whether our data actually follows a specific distribution. Can you remind us why this is even important in the first place?
Knowing the distribution of your data is really crucial for selecting the right statistical methods for your analysis. A lot of those methods rely on assumptions about the data's distribution, and if those assumptions aren't met, your results can be misleading.
So it's like making sure you're using the right tool for the job.
Exactly. You wouldn't use a hammer to screw in a screw. In statistics, choosing the right tools depends heavily on the characteristics of your data, and its distribution is a key part of that.
You mentioned a visual technique called probability plots. Can you refresh our memory on how those work and what they can tell us?
Probability plots are a great way to visually assess whether your data seems to follow a specific theoretical distribution. You basically plot the quantiles of your data against the quantiles of that theoretical distribution you have in mind. If the points line up nicely, it's a good sign that your data might be following that distribution.
It's a quick visual check to see if things look right. But what if we need something more rigorous, something quantitative, to test that goodness of fit?
That's where those statistical tests come in handy. The Anderson-Darling test, which we discussed earlier, is really good at detecting even subtle deviations from normality. It's like a high-precision instrument that can pick up on tiny inconsistencies in the data.
And you mentioned Minitab and ML estimation earlier. Can you give us a bit more detail about how those tools can help us identify data distributions?
Sure. Minitab, as we mentioned, is a statistical software package. It's like a Swiss Army knife for data analysis, and it includes tools for doing those goodness of fit tests. And ML estimation, which stands for maximum likelihood estimation, is a method for finding the parameters of a specific distribution that would best fit the observed data.
So those tools can help us identify the most likely distribution for our data, which then guides us in choosing the appropriate statistical methods for further analysis.
Right. It's all about laying a solid foundation for your analysis.
Now, going back to our discussion on standard error, I'm remembering that counterintuitive point you made. The standard error of the median can sometimes be larger than the standard error of the mean, even though we often think of the median as being more robust to outliers. Can you walk us through that again?
Absolutely. It's a great reminder that we need to think about both the measure itself, the median in this case, and the way we calculate its standard error. The median might not be drastically affected by outliers, but the bootstrapping method, which is often used to estimate the standard error of the median, can introduce variability. Remember, bootstrapping involves creating those mini data sets from our original data and then calculating the median for each of those.
So it's like running those simulations to see how much the median jumps around.
Exactly. And because we're creating those mini data sets by randomly sampling from the original data, outliers might be included or excluded randomly in those samples. That can cause the medians to vary quite a bit, leading to a larger standard error.
So it's not just about whether the measure is sensitive to outliers, it's also about the variability introduced by the method we use to estimate the standard error, an important nuance.
Definitely. It emphasizes why it's so important to understand the underlying mechanics of the statistical methods we're using.
You also mentioned improving two-factor ANOVA using a randomized block design. Can you remind us how that technique helps us get more meaningful results?
Of course. Let's imagine we're studying the effects of two different teaching methods on student performance. We know students come into the study with different levels of knowledge, right? If we just randomly assign students to those different teaching method groups, all that variation in their existing knowledge could actually mask the true effects of the teaching methods.
It's like starting a race where some runners are already a mile ahead of the others. Wouldn't be a fair comparison.
Right. A randomized block design is kind of like grouping the runners based on their starting point and then randomly assigning them to different running strategies within those groups. So for the students, we would first group them based on similar levels of knowledge, and then we'd randomly assign them to different teaching methods within those knowledge blocks. This reduces the variation within each teaching method group, making the comparison between those methods much more accurate.
So we're basically controlling for a factor we know might be influencing the results, allowing us to better isolate the effects we're interested in.
Exactly. It helps you see the signal more clearly.
Now, shifting gears again, let's talk about overfitting in linear regression, a common trap in data analysis. You mentioned a scenario with 1,000 samples and 900 features. What's the potential issue there?
That's a perfect illustration of what can happen when you have too many features relative to the number of samples. It's like trying to write a 10-page essay based on just one paragraph of information. You're going to end up stretching that information too thin and making connections that aren't really there.
So the model ends up picking up on noise rather than the real signal, which can lead to bad predictions when you try to use it on new data.
Right. It's like that student who crams for a test by just memorizing answers without understanding the concepts. They might do well on that one test, but that knowledge won't apply anywhere else.
And you mentioned some techniques to help us avoid this overfitting trap: Lasso, Ridge, and Elastic Net. Can you break those down a bit?
These techniques add a penalty to the complexity of the model. They're like saying, hey, model, don't get too excited about every little detail. Keep things simple. It's like adding a bit of friction to the model fitting process to prevent it from going overboard.
So it's about finding that sweet spot, a model that fits the data well but is also simple enough to generalize. Can you give us a bit more detail on how Lasso and Ridge differ in their approaches?
Sure. Lasso, which uses L1 regularization, can actually force some of the coefficients in the model all the way down to 0. That means it can do what we call feature selection. It picks out the most relevant features and gets rid of the less important ones.
So it's like simplifying the model by identifying the most important ingredients. What about ridge regression? How does it tackle the problem?
Ridge regression uses what we call L2 regularization, and it's a bit more gentle. It doesn't force coefficients to 0, but it shrinks them proportionally, so all the features can still make a contribution, but no single feature gets to be the star of the show.
Okay, so both techniques are aiming for simplicity, but they get there in different ways. Now, you also raised a really interesting point about comparing means. You asked, is it enough to just compare the average price of shoes from last year to this year to see if prices have changed? Why might that be a risky move?
That question highlights the importance of thinking about the context of your data. As your notes mention, shoe prices aren't all the same. They vary based on brand, style, you name it.
It's like trying to compare apples and oranges, especially if the mix of fruit in the basket has changed between the 2 years you're comparing.
Right. If the types of shoes being sold this year are different from last year, comparing those overall average prices could be really misleading. For example, what if there's a sudden surge in demand for those pricey designer sneakers this year? The overall average price might go up, even if the prices for other types of shoes have stayed the same.
That makes a lot of sense. So how can we get a more accurate picture of price changes when we have all of this variation within our data?
T-tests to the rescue. They let you compare the means of subgroups, giving you a more granular view of the data. Instead of looking at all shoes, you could compare, say, the average price of men's running shoes this year to the average price of men's running shoes last year. You can do that for different categories.
So we're basically accounting for those confounding variables, like the different types of shoes, to get a clearer picture of what's really happening with prices within each category.
Exactly. It's all about recognizing the structure of your data and analyzing it at the right level of detail.
Now, let's move on to a topic that's crucial for planning good research: power analysis. I know you're all about learning quickly and efficiently. How can we break this down in a way that's both easy to grasp and memorable?
Power analysis, at its core, is about figuring out your chances of finding a statistically significant effect if there really is one. It's kind of like planning a fishing trip. You want to make sure the sample size is big enough and you have the right bait, the study designed to actually catch the fish, which is the effect you're looking for.
And to avoid coming back empty-handed from our fishing trip, we've got to understand those type I and type 2 errors.
You got it. I love that analogy you use. Convicting an innocent person, a type I error, or letting a guilty person go free, a type 2 error.
So a type I error in research is like concluding that there's an effect when there really isn't,
Hmm.
and a type 2 error is like missing a real effect. Power analysis helps us find a good balance between those two types of errors.
Exactly. It guides us into making good decisions about the sample size we need and the overall design of the study.
You mentioned the key parameters we need for power analysis: significance level, effect size, and power. Quick reminder, what do those represent again?
Sure. Significance level, often called alpha, is like setting the threshold for how strong the evidence needs to be before we reject that null hypothesis. It's the probability of making that type I error, concluding there's an effect when there really isn't.
So it's about how convincing the evidence needs to be before we say, okay, this is a real thing. What about effect size? How does that fit in?
Effect size is all about how big the effect is that we're trying to find. The larger the effect, the easier it'll be to detect, even with a smaller sample size.
So it's about the strength of the signal and the data. And lastly, what about power itself?
Power is the probability of correctly rejecting the null hypothesis when it's actually false. Basically, it's your chance of finding a real effect if one exists.
Okay, so power analysis gives us a way to make sure our study is set up for success. We decide on the level of power we want, consider the expected effect size, and then we can calculate the sample size we'll need to make it all work.
It helps you avoid those fishing expedition failures.
Okay, let's apply this to a simple scenario. Testing if a coin is fair. You asked this. You flip a coin 10 times and get 8 heads. Does that automatically mean the coin is rigged?
Well, it might seem that way, but 10 flips, it's not really that many. Just like with the fishing analogy, sometimes you can get lucky even if the lake isn't teeming with fish.
So statistically, how do we figure out if the coin is truly biased or if we just got a bit lucky?
We need to look at the probability of getting 8 or more heads, even if the coin is perfectly fair. If that probability is pretty high, then chance is a reasonable explanation. But if it's very low, then yeah, we might start to suspect that the coin isn't playing fair. We can calculate that probability using the binomial distribution, which tells us how likely it is to get a certain number of successes, like heads, in a set number of trials.
Okay, so we could use that to see how unusual our result is, assuming the coin is fair. And if we want to be even more rigorous, we can do a t-test, right, to formally test that hypothesis that the coin is fair.
Right. A t-test makes sense here because we're comparing the proportion of heads we observed, 8 out of 10, to the proportion we'd expect if the coin was fair, 0.5 or 50%.
That's a great illustration of how we use hypothesis testing in practice. Now, you've also touched on a topic that often causes a lot of confusion: causal inference. Specifically, You asked whether randomly sampling 1,000 people in Mountain View and doing an ANOVA would be a valid way to determine if going to college actually causes higher income.
That question hits on a crucial point. How do we prove causation, not just correlation? Just because we see a relationship between two things, like going to college and earning more money, doesn't mean that one causes the other. There can be all sorts of other things influencing both.
So what's the problem with that approach, random sampling in Mountain View and then doing an ANOVA?
Well, for starters, Mountain View, as we discussed, isn't necessarily representative of the whole population. It's a unique place, lots of tech, high salaries. That could really distort the results.
Right, so sampling bias is something to be very mindful of. What else should we watch out for?
We've got to be super careful about those confounding variables, those sneaky factors that influence both going to college and earning more money. They can make it really hard to isolate the effect of college alone. Family socioeconomic status, as we mentioned earlier, is a classic example.
Right, kids from more affluent families are more likely to go to college, and they might also have advantages that lead to higher earnings, regardless of their education.
Exactly. So the connection we see between college and income might be what we call spurious. It might look like a cause and effect relationship, but it's actually driven by those hidden factors.
So how do we try to tease apart all of those influences? Especially when A/B testing, which is often considered the gold standard for proving causation, isn't feasible.
Well, in those cases, we rely a lot on observational studies and statistical methods that try to control for those confounding variables as best as we can.
It's like trying to filter out all that extra noise to get a clearer picture of the true signal.
Exactly. And while it might not be perfect, these techniques can definitely help us get closer to the truth.
Now, let's switch gears and dive back into the world of identifying data distributions. You've mentioned several techniques for figuring out whether our data actually follows a specific distribution. Can you remind us again why this is even important in data analysis?
It's all about choosing the right statistical methods for the job. Lots of those methods depend on certain assumptions about the distribution of the data, and if those assumptions aren't met, your results could be misleading.
So it's like making sure we're using the right tools for the task at hand.
Precisely. Just like you wouldn't use a hammer to screw in a screw, you wouldn't use a statistical test that assumes normality if your data doesn't actually follow a normal distribution.
You mentioned probability plots as a way to visually assess whether our data fits a particular distribution. Can you remind us how those work?
Sure, you're basically comparing the quantiles of your data to the quantiles of the theoretical distribution you have in mind. If the points on the plot fall roughly along a straight line, it's a good indication that your data might be following that distribution.
So it's a quick visual check to see if things look right. But sometimes we need something more quantitative to test that goodness of fit.
That's where those statistical tests come in. The Anderson-Darling test, for example, is great at catching even subtle deviations from normality.
And you also mentioned Minitab and ML estimation earlier. Can you tell us a bit more about those and how they relate to figuring out data distributions?
Of course, Minitab, as we said earlier, is a statistical software package. It's packed with tools for data analysis, and it includes a bunch of options for those goodness of fit tests. ML estimation, or maximum likelihood estimation, is a method for finding the parameters of a specific distribution that best fit the data you have.
So those tools can help us figure out which distribution our data is most likely following, which is crucial for choosing the right statistical methods for further analysis.
It's about setting the stage for a solid and trustworthy analysis.
Now, thinking back to our conversation about standard error, I'm remembering that interesting point you made. The standard error of the median can sometimes be bigger than the standard error of the mean, even though the median is often thought of as more resistant to those outliers. Can you walk us through that again?
Yeah, that's a really good example of why it's so important to think about both the measure itself and how we actually calculate its standard error. The median might not be super affected by outliers, but that bootstrapping process we often use to estimate the standard error of the median, well, that can introduce some variability. Remember, with bootstrapping, we're creating those mini data sets from the original data and calculating the median for each one.
So we're kind of simulating a bunch of scenarios to see how much the median fluctuates.
Exactly. And since we're creating those mini data sets by random sampling, those outliers might pop up in some samples and not in others. That can make the medians of those samples vary quite a bit, which leads to a larger standard error.
So it's not just about whether the measure itself is sensitive to outliers. It's also about the variability that comes from the method we use to estimate that standard error. Interesting stuff.
It really is. It highlights why it's so important to have a good understanding of what's happening under the hood with those statistical methods.
Okay, you also mentioned a technique for improving two-factor ANOVA using a randomized block design.
hmm
Can you remind us how that helps us get those more meaningful results?
Let's say we're researching the effects of two different teaching methods on student performance. But, students come in with different levels of prior knowledge, right? If we just randomly assign students to those teaching method groups, all that variability in their starting point could actually obscure the real effects of the teaching methods.
Yeah, it'd be like having some runners in a race starting a mile ahead of the others. It wouldn't be a fair comparison at all.
Right. A randomized block design is like grouping the runners based on their starting position and then randomly assigning them to different running strategies within those groups. So for the students, we would first group them based on similar levels of knowledge, and then we'd randomly assign them to different teaching methods within those knowledge blocks. That reduces the variation within each teaching method group, making the comparison between the methods much more accurate.
So it's a way to control for something that we know might be influencing the results, letting us see the effects we're interested in more clearly.
Exactly. It helps you isolate the signal from the noise.
Now let's talk about a common pitfall: overfitting in linear regression. You mentioned a scenario with a data set that has 1,000 samples and a whopping 900 features. What's the problem there?
That's a classic case of having way too many features compared to the number of samples. It's like trying to write a 10-page essay based on a single paragraph. You're going to end up stretching that information way too thin and making connections that just aren't really there.
So instead of capturing the real patterns in the data, the model ends up memorizing all the random noise. And that leads to terrible predictions when you try to use the model on new data.
Exactly. Imagine that student who crams for a test by memorizing the answers without understanding the material. They might do great on that one test, but that knowledge isn't going to transfer to any other situation.
Makes sense. And to avoid falling into that trap, you highlighted some techniques: Lasso, Ridge, and Elastic Net. Can you remind us how they help us prevent overfitting?
These techniques basically penalize the model for getting too complex. It's like adding a bit of friction to the model fitting process so it doesn't get carried away.
So it's about finding that balance. We want a model that fits the data well, but is also simple enough that it can actually be useful with new data. Can you tell us a bit more about how Lasso and Ridge differ in their approaches?
Lasso, which uses what we call L1 regularization, has this interesting ability to actually force some of the coefficients in the model down to zero. What that means is it can do feature selection, it identifies the most important features, and essentially throws out the ones that aren't contributing much.
So it's like simplifying the model, making it leaner and meaner. What about ridge regression? What's its style?
Ridge regression uses L2 regularization, and it's a bit gentler. Instead of forcing coefficients to zero, it just shrinks them proportionally. That way, all the features can still contribute, but no single feature gets to dominate the model.
Okay, so they both aim for simplicity, but they take different paths to get there. Now, you also had a thought-provoking question about comparing means. You asked, can we just compare the average price of shoes from one year to the next to see if prices have changed? Why might that approach not be so straightforward?
That question really highlights the importance of taking a close look at the structure of your data. As we've discussed, shoe prices aren't all created equal. They vary a lot depending on the brand, the style, all those factors.
Right, it's like trying to compare apples and oranges, especially if the types of fruit in the basket have completely changed between the 2 years you're comparing.
Exactly. If the mix of shoes being sold this year is different from what was being sold last year, comparing those overall averages could lead you to some pretty inaccurate conclusions. For instance, what if there's a big increase in the demand for those expensive designer sneakers this year? The overall average price might go up, even if the prices for other types of shoes haven't budged at all.
That makes perfect sense.
Yeah.
So how can we get a more reliable picture of those price trends when there's so much variation within the data?
T-tests are a really helpful tool in this situation. They allow you to compare the means of different subgroups, giving you a more detailed view of what's happening. Instead of just looking at all shoes together, you could compare, for example, the average price of men's running shoes this year to the average price of men's running shoes last year, and you can do that for other categories as well.
So you're essentially controlling for those confounding variables, like the different types of shoes, to get a clearer picture of the real price trends within each category.
Exactly. It's about understanding the structure of your data and analyzing it at the right level. It's been great diving into all of these statistical concepts with you.
It really has. We've covered so much ground, from understanding those fundamental concepts like standard error to tackling those trickier challenges of causal inference and really mastering those estimation techniques. It's incredible how interconnected all of these concepts are and how powerful they can be when it comes to making sense of data.
Absolutely. Statistics provides us with such a valuable framework for understanding and navigating a world that's just overflowing with data. And as we've seen today, it's a world full of surprises.
We've only scratched the surface, but I hope this deep dive has given you a solid foundation and, maybe even more importantly, sparked some new questions. Remember, the most exciting knowledge isn't just what's in the textbooks. It's what you discover when you go out there and explore the data yourself. So, happy analyzing.